IGCSE Computer Science, Syllabus Statement 1.3.5a, describe the principles of operation of RAM and ROM. So this is what we're going to do in this video. We're going to look at, oh, my chair's a bit, yeah. So we're going to look at two types of RAM. We're going to look at static RAM and dynamic RAM, and then we're going to look at ROM, and then we're going to look at how both of them are applied to a given application. So let's get started. Oh yeah, one other thing. This video is, well, RAM and ROM is pretty much primary memory. And then the next two videos are going to be secondary storage, and then the next, I think, 2 or 3 videos are going to be offline storage. So yeah, that's pretty much how it's going to go. So let's start with RAM. So random access memory is volatile memory used to store data files or part of an operating system which are currently in use. It can be read from and written to. So it's important here, currently in use. So data files are part of an operating system which are currently being used. I don't know how else to explain it. Yeah, so it's important to keep that in mind because random access memory is volatile. And what that means is it's temporary memory. So the contents of RAM are lost when the power to the RAM is turned off. Yeah, so it doesn't stay there. So it's important to know that it's just stuff that's currently in use. So this is what RAM looks like. This is dynamic RAM and this is static RAM, and we're going to look at the differences right now. Before that, we should look at introduction. So the larger the RAM, the faster the computer will run. It's a general... Yeah, so RAM never runs out, but it gets slower through time. And you may notice this, because if you have a computer, it gets slower through time. So, yeah. As RAM becomes full, the processor has to access the hard disk drive, or HDD, to replace old data on the RAM with new data. But by increasing the RAM size, the number of times this access operation is done is reduced, and this makes the computer run faster. So you can think of it like, well, actually before that, I should probably say that HDD, or a hard disk drive, is secondary storage. So when the primary memory, the RAM, gets full, then the processor can't keep adding data to the full RAM. I mean, how can it if it's full? So it's going to have to replace old data with the new data somehow. So it's going to have to access the hard disk drive on the computer to do that. So yeah, let's finally look at DRAM. So dynamic RAM is made up, dynamic RAM chips are made up of numerous capacitors and transistors. A capacitor is something that holds a bit of information, so 0 or 1. And a transistor is kind of like a switch. It allows the control circuitry on the chip to read from or write to a capacitor. DRAM needs to be refreshed constantly. So this means that capacitors need to be recharged, and this usually happens every 15 microseconds. If they aren't, they will lose their charges and their values would be zeros, and that's pretty annoying. Static RAM is a bit different. Unlike dynamic RAM, static RAM doesn't need to be refreshed. Instead of capacitors and transistors, static RAM makes use of flip-flops to hold bits of memory. And static RAM also provides faster access speed. So typical DRAM access speed is 60 nanoseconds. It's pretty damn fast, actually. While the SRAM access speed is 25 nanoseconds, even faster. Because, we work with seconds in this world. We see a clock and we say, okay, this lesson's going to end in a few minutes. That's longer than seconds. But, then there's seconds, and then there's milliseconds, and there's microseconds, and there's nanoseconds. Whoa. So let's look at advantages of DRAM. It's less expensive to manufacture, it consumes less energy, and it has a higher storage capacity. Advantages of static RAM: doesn't need to be refreshed, data access is faster, and that's it. You could probably think of a few more if you look online, but this is pretty basic understanding of the advantages and the advantages of DRAM and SRAM. So let's look at ROM. So read-only memory is a non-volatile memory used to store the startup instructions for a computer system. So like the basic input-output system. It can only be read from, so it can't be written to. However, data isn't lost when you turn the power off. It stays. So ROM kind of looks like RAM, but it's not. It's not RAM. Anyway, so that's pretty much it. That's all you really need to know about ROM, but to better understand it, we have to look at an application. So a toy car has a circuitry which contains RAM and ROM chips. The ROM chip stores the factory settings, startup routines, and the RAM chip stores the instructions sent from the controller, so what's currently being used. Additionally, if the car contains a solid-state drive, it can be used to store the instructions to operate the car. A suitable input device such as a touchscreen or keypad can be used for the controller, and the reasons for this are touchscreens and keypads are easy to use, and there are a limited number of options. So let's go back here, because I think I kind of rushed this. So the ROM, remember, is read-only memory, so you store stuff in it. Like, you just, when you make the toy car, you put the startup instructions, whatever, inside that ROM chip. So it's only read from, it's never written to. So that's pretty much what starts up a toy car. The RAM chip stores whatever is currently being used, so the instructions sent from the controller. And yeah, that's pretty much it. There's nothing much to know about, but hopefully you get an understanding of how this works. And as for this, you're going to learn about how solid-state drives work in 2 videos from this one, so I'm not going to talk about that. And as for suitable input devices, well, we looked at input devices, and the reason why we shouldn't really use a keyboard or a mouse is because with a keyboard we have all these buttons when we really only need, I don't know, move forward, move backwards, turn left, turn right. That's pretty much it. Maybe increase speed. So a touchscreen would be suitable because, you know, there aren't that many buttons, like maybe 5 or 6. Like a keyboard has quite a bit. So yeah, it's suitable to use a touchscreen or keypad. And also, they're easier to use because with a touchscreen, you know, you're seeing a button that says, like, you know, move forward or like an arrow or something like that. So simple to use. So yeah, that's pretty much it. IGCSE Computer Science, syllabus statement 1.3.5b. And actually, before we continue, 1.3.5b is actually pretty short when I look at it. It's shorter than output devices or input devices, but it's still stuff to learn, yeah, but still quite short. So, and actually, the next topic, which is operating systems, is much shorter. It's not really just operating systems. It's more of operating systems, interrupts, buffers, and all that. And then there's high, low-level languages, which is only going to take like 2 videos. So we're pretty much almost done with topic 3. We just have this one, then solid state, and then optical offline, and then magnetic and solid state offline as well. And then we have operating systems, and then we have interrupts and buffers, and then we have high, low-level languages, and then we have translators, and that's it for topic 3. We're almost there, guys. Alright, so I think I've wasted enough time talking about that. Let's jump into HDDs. So, hard disk drive is a common secondary storage method which makes use of magnetic disks to store data. So basically, what happens is data is stored in a digital format on the magnetic surfaces of the disks, or we're going to refer to them as platters, because that's what they're usually called. They kind of look like this, and as you can see, if you can see really closely here, these are read-write heads, and you can see that there are a number of them, which means that there are a number of platters here, but you can't really see that. So a typical hard disk drive will have a number of platters, which can spin around 7,000, I don't know, 7,000 times per second. Usually each platter has two surfaces to store data. A number of read-write heads have access to the surfaces of the platters, and typically they can move from the center of a platter to the edge and back again 50 times a second. I don't know if I should consider that fast, because I mean physically it is fast, but it can be slow, and we'll look at that. On the platters, data is stored in sectors and tracks. Each sector has a fixed number of bytes. Now it's important that we know what we mean by sector. So let's look at a platter. So here we have A, B, C, and D. So A is the track, the pink thing right here. B is the geometrical sector. Now, this is what we mean. Here's the confusing part. Now, we mean this is the geometrical sector. So if you imagine a circle, this would be the sector of a circle. But we don't mean geometrical sector when we say sector in platters. We mean the track sector right here, this small part right here, the sector of a track. So that's what we mean by sector. So instead of like sectors like these, we have sectors like these. So we have a bunch of sectors for each track. And that's what we mean by that. And just to avoid any confusion. And D is a cluster, but we don't need to know about that. The real disadvantage of HDDs is latency. Now, latency is pretty much the time taken for a block of data on a track to rotate around to the read-write head. And this is a disadvantage because since many applications require the read-write heads to look for the correct sectors to read or write data, a big number of head movements are required. Does that make sense? A big number of head movements are required. I don't think that makes sense. It should be a big number of head movements is required. Anyway, you get the point. So, you may notice this effect when you see messages such as "please wait" or "not responding." So that there you can see an effect of latency, because it takes time to write data, and in extreme cases, it doesn't really respond. So that's pretty much it for hard disk drives, and we'll look at solid-state drives in the next video, and we're going to see how they avoid this latency problem. Hi, GCSE Computer Science. Still the same at 1.3.5c. This is to describe the principles of operation of solid-state drives. So, in the last video, we looked at hard disk drives, and how they, a disadvantage of them is latency. So, now we'll look at solid-state drives, and we'll see how they are a lot better. So, a solid-state drive is another secondary storage method, and this makes use of controlling the movement of electrons, which is pretty cool. So, on the inside of a solid-state drive, it may look like this, which I got online, but tell me if it's false, because I just searched these up on Google Images. I don't actually. Anyway, so solid-state drives, as said, solid-state drives remove the issue of latency, which hard disk drives have. And solid-state drives also have no moving parts, and all data is retrieved at the same time, or at the same rate, rather. At the same time, that would be quite. Most SSDs use flash technology, and what this means is that data is stored by controlling the movement of electrons within NAND chips. So you remember the NAND gate, then yeah, you can pretty much think of it like that. Data is stored as ones and zeros in millions of transistors in each chip, and this creates non-volatile, rewritable memory. And we looked at We looked at volatile RAM. We looked at non-volatile ROM. Non-volatile ROM couldn't be written to, and RAM could, but RAM was volatile. So if you turn the power off, then well, all the data would be lost. So now we have non-volatile rewritable memory. And this is pretty cool stuff. Some SSDs also use EEPROM technology. And this means that data is stored by controlling the movement of electrons within NOR chips. And so note the difference, NAND and NOR. And this makes them faster in operation, but more expensive than flash technology. Now if you remember, back when we looked at logic, we talked about logic building blocks. Now, NAND and NOR gates are logic building blocks. With NAND or NOR gates, you can build any other logic gate. However, we usually use NAND because it's a lot cheaper. So that's why most people prefer NAND. And this is kind of the same idea here. NOR is more expensive, so this technology is more expensive. EEPROM technology also allows data to be read or erased bytes at a time, while flash technology only allows data to be read in blocks. So we'll look at advantages of SSDs over HDDs, so it's sort of a summary plus a few other things thrown in. So faster data access, yep. More reliable, no moving parts. So this is a good one because we look at hard disk drives and we see that these platters are moving. These read-write heads are moving. But with solid-state drives, nothing's really moving. There are no moving parts. And if you remember the toy car that we looked at in primary memory video, here's an advantage of using solid-state drives for the toy car. And this no moving parts allows them to be very thin. It also allows them to be lighter in weight, if it's very thin, because, you know, the thinner, the lighter usually. There's also no need to wait for them to operate at full speed, and they don't heat up as much as, again, other advantages of using solid-state drives in the toy car. So, yeah, that's pretty much it for solid-state drives, and we can finally move on to offline storage in the next video. IGCSE Computer Science, Syllabus Statement 1.3.5D, describe the principles of operation of optical offline storage systems. So, an optical storage is the storage of data on an optically readable medium. So we're going to look at, for these devices, we're going to look at CDs, DVDs, DVD RAMs, and Blu-ray discs. So we'll move on to solid-state and magnetic storage devices, and then that's it for no, not quite. We still have to look at file sizes again. But anyway, let's go ahead and get started. So CDs and DVDs, compact discs, and digital versatile discs are examples of optical storage devices. Both CDs and DVDs use a thin layer, or layers as you're about to find out, of metal and light-sensitive organic dye to store data. Both of them also use a single spiral track, which runs from the center to the edge of the disk. It's kind of like this. You have a spiral, On the track, data is stored as pits and bumps. A red laser is used to read and write data. Both CDs and DVDs can be designated an R for write once, or RW, read and write multiple times. So a DVD, however, differs slightly from a CD. A DVD can have two layers, which increases its storage capacity. The two layers are joined together with a transparent polycarbonate spacer and a thin reflector. But single-layer DVDs still have a larger storage capacity than CDs because the pit size and track width are smaller. Also, DVD layers have shorter wavelengths. The shorter the laser wavelength, the greater the storage capacity. We actually don't really see CDs and DVDs that much anymore. Like, I mean, I still have Blu-ray discs, but that's about it. Like, I never actually have seen a DVD for quite a while. Um, but anyway, let's carry on. We'll talk more about that later. So here's how DVDs kind of look, if you were wondering. So we have a laser beam that reads this part here, and a laser beam that reads this part here. So it's semi-transparent metal reflector, which means that it's semi-transparent, which basically means that a laser can pass through it. How this works is the laser sort of changes itself to, like, sort of focuses in order to read the second layer. So in order to pass through this semi-transparent layer to read this layer here. And that's pretty much how it works. Now, there is a disadvantage to this, which we will look at later. So then there's DVD RAM, and DVD RAM is quite different. Everything's different around here. It uses a number of concentric tracks instead of a single spiral track, and this allows simultaneous read and write operations as well as faster data access. They also have a greater longevity, is that how you pronounce it? Longevity, I think it's longevity. It's usually over 30 years, and this makes them ideal for archiving data. Blu-ray discs are different to the others. They use a blue laser to carry out read and write operations, and the wavelength of blue light is shorter than red light, and if you remember, the shorter the wavelength, then the larger the storage capacity. Using a blue laser also allows the pits and bumps to be smaller, which allows more data to be stored. Blu-ray discs have a single polycarbonate layer, which avoids, that's what I was talking about, birefringence. Well, actually, I'll just say this first, because I might as well. I forgot the little title there. Blu-ray discs come with a secure encryption system, which helps prevent piracy and copyright infringement. Birefringence. Well, if you're familiar with refraction of light, then what birefringence is the refraction of the laser. So there are two separate beams, and this causes reading errors. So that may happen, and that's the disadvantage of using DVDs with two layers. So, yeah. So let's look at just a summary of all the features of each disc that we looked at, except for DVD RAM, because it's yeah. So CD, I mean, when we say DVD RAM, we kind of mean, like, DVD, but with concentric tracks. So never mind that. Okay, so CD, laser color red, wavelength 780 nanometers, disc construction, single polycarbonate layer 1.2 millimeters, and track pitch. Now, what do we mean by track pitch? Well, track pitch is pretty much the distance between each track. So, track pitch of CDs is 1.6 micrometers. Is that micro? Yeah, it's micro. So the U thingy. DVDs, laser color red, wavelength 650 nanometers, disc construction, double polycarbonate layer, each layer is 0.6 millimeters, which of course adds up to 1.2 millimeters. And the track pitch is 0.74 micrometer. I keep forgetting it's a micrometer. Oh, I forgot a space between this. Makes me cringe. Blu-ray discs, laser color blue. Oh, it's totally different now. Wavelength is 405 nanometers. Use a single polycarbonate layer, 1.1 millimeters, effectively making it, not really effectively, I don't think, but makes it much thinner layer than these two. And the track pitch is 0.30 micrometers. I wish I didn't put that space there. I mean, I wish I did put the... Now, I wish I put the space here, here. No, hang on. I mean, I wish I put the space here and here in order for everything to make sense. Alright. Anyway, that's pretty much it for optical offline storage systems. And before we go, we need to think about the future. Now, we are noticing that most people nowadays watch Netflix and chill. And, like, they don't really, they don't really use CDs or DVDs anymore unless they're my parents. Now, here's the thing. Like, we use a lot of our smartphones and tablets, laptops, and whatever to store our data. We don't really use CDs and DVDs anymore. Although Blu-rays are still pretty popular, I think. There's, but like CDs and DVDs, not really. And, well, yeah, we need to think about how data will be stored in the future. And it's like, if you remember the floppy disks, really, like, way back, we don't ever see these anymore. So the same thing may happen to CDs, DVDs, and even Blu-ray. And of course, they might be replaced with what we're looking at now. So, like, stored in your devices, stored on hard disk drives, stored in, well, there's the cloud as well. Like, we have Google Drive, Apple Cloud. We have all of this cool stuff. We have the internet. We can store, like, I'm storing my videos on YouTube right now. Like, I'm not storing these on my laptop. I'm storing them on YouTube. Once I'm done recording and uploading, I delete them. No, actually, that's not entirely true. I keep them just in case my channel gets destroyed. I keep them in my hard drive, actually, which is, I don't know if it's solid state or not. Let me check. Actually, I can't be bothered to get it. But anyway, the point is, like, we're seeing a lot of advancements. Like we looked at the advancements of LED monitors to OLED. And that's quite cool, because, like, I mean, we haven't really seen that a lot yet, but we may actually see this in the future. I feel like I'm giving a speech. I actually kind of am giving a speech, but it's off the top of my head, so it's kind of hard to actually think of what to say. But yeah, anyway, that's pretty much it for this video. And yeah, thanks for watching. And yeah, I hope you find this whole futuristic stuff really cool. GCSE Computer Science. This is syllabus statement 1.3.5e. This is the principles of operation of, actually, to be honest, we're not really seeing how magnetic and solid state systems work. We're seeing how they are applied to offline storage. So how they're applied to, like, external hard drives, how they're applied to, like, thumb drives or memory sticks or XD or SD cards. So that's pretty much it. So we have we have magnetic here, the hard drive, and we have solid state here, the thumb drive, the XD card, and the SD card. So we're going to see how they work. Now, obviously, solid state's going to be a bit longer than magnetic, because magnetic, we're only looking at one device. Solid state, we're looking at 3. Just keep that in mind. So magnetic offline storage systems. Now, we know how the principles of operation. We know the principles of operation of like magnetic secondary storage stuff, platters, stuff like that. So we don't really need to look at that. We just need to think about the external hard disk drives. So when hard disk drives are external, they can plug into computers or other devices. So when we're looking at secondary storage, we were looking at the storage on a device, the storage on a, like, say, laptop. When we're talking about external hard drives, we talk about ones that plug in. And they're usually used for backup or transfer of large files between devices. Now, backup's quite important, because when we move on to the security topic, which we're going to do pretty soon, you're going to see that like accidental, like, loss or damage of data can be really, like, can have a large impact if your files really matter. If you're writing an extended essay in IB, and you've already gotten 4,000 words down, you're just like, yeah, I'm done with this. I'm through with this. Let's finish it. And then your computer falls into a river. Well, it's going to be a lot of work. So yeah, it's good to back up, and we'll see more on that in security. Also, just a quick note, I forgot to mention this in the optical storage video. CDs and DVDs and Blu-ray discs can be used as backup. And yeah, that's pretty much it. That was a bit awkward. No, yeah, whatever. Solid-state offline storage systems. So devices such as memory sticks, XD or SD cards use solid-state technology. And like external hard drives, they plug into other devices. Now, they're solid-state technology, which means that they are made up of NAND gates, not chips rather. NAND gates, it doesn't really matter. It's NAND technology, right? And they store information by controlling the movement of electrons, and there are no moving parts. There are a few advantages of these devices, such as they are small, they are light in weight, and they are portable. And this makes it easy to transfer files between devices. Also kind of makes them, I wouldn't say it makes it easier to like back up. It could, because like you could store really small small devices into like your little purse or little bag or whatever, or your drawers. So yeah, I guess that kind of uses of memory sticks. So one use of a memory stick is using it as a dongle. Actually, we're only looking at one use of memory sticks, like one important use that we need to look at. Usually complex or expensive software does this, and a dongle will contain additional files needed to run the software. And this prevents unauthorized use of the software, since without the dongle, the software wouldn't work. So, we have, like, someone steals software, they don't have the dongle, so how the hell are they meant to use that software? That's quite a smart thing to do. Uses of XD or SD cards. So a use of XD or SD cards is to save photos in digital cameras. They are thinner than memory sticks, as you saw in the first slide, which allows them to fit inside cameras. So instead of having a memory stick sticking out of the camera, we have something that goes in the camera, so less chance of it falling out. They can also be used to transfer the photos, the camera, to another device. Some devices have XD or SD card slots, like my old computer did. My new computer doesn't, because we don't use that stuff anymore. Now, what usually happens is cameras can, still use XD or SD cards, but the transfer of files is usually done by using a USB port and USB. And transferring the files to the computer. So one end plugs into the camera, one end the USB plugs into the computer, and that's how it's done. So that's pretty much it for memory. The next video we'll look at a really easy topic. Don't worry about it. It's nothing much to learn. It's just like file sizes again. So we're kind of relearning what we learned back in topic 1. So when we looked at like JPEG compression, sort of stuff like that. But you're sort of given like text or a photo, you're given some information about it, you calculate the size. It's really simple. So thanks for watching, and I'll see you guys when I see you guys. GCSE Computer Science, Syllabus Statement 1.3.5F, and this video is going to be quite chill. So calculate the storage requirement of a file. As said in the previous video, actually, my room's gotten dark. Give me a second. I'm just going to turn my lights on. Anyway, I'm going to walk and talk. Anyway, so, I said anyway a lot. Okay, so, text files. So, we're looking at the storage requirement of 2 types of files. We're going to be looking at text files and, image files. Yeah, that's it. Anyway, so let's look at a text file. So we have a text file here saying calculate the size of this file. So here's how we can do it. So if you remember, 31 characters. This 31 characters including spaces. Each ASCII character has a value of 1 byte. So would the file be 31 bytes? Well, let's have a look. Ooh, size 31 bytes. So yeah, that's true. It worked. Yay. That's pretty much, yeah. I know it says 4 KB on disk, and it's because there's a lot of other code involved in this, but we're not concerned about that. We're concerned about the actual size of the file. Image files. So here we have, oh, kittens. We have 4 little kittens here. And this is a BMP image file. So this image is 1600 by 1200 pixels. Now if you remember, we do this. So 1600 times 1200 times 3, which gives 5,760,000 something like that bytes. So would the file be that many bytes? I'm just going to check if I did my calculation right. 1,000 times 3. I hope it's right. Don't want to scrap this video. Yeah, it is. Alright, so would this file be this many bytes? Well, let's have a look. And again, this is a BMP image, which I called cat.bmp. And as you can see, 5,760,138 bytes. So close enough. And again, the size may vary due to other code. So, yeah. We're pretty much close enough. So you get the idea, right? So if they ask you a question like that in the exam, estimate the file size of this, then you can do that. Alright, so let's try a question. So text is to be stored in a document. So I got this quote from Mark Zuckerberg. Calculate the file size required to store this document. So what you do is count the number of characters in the sentence. So the text has 109 characters. Each character is 1 byte. So the file size should be 109 bytes. Let's try an image file. So an image question. So a BMP photo is 1024 by 512 pixels. Calculate the file size of this image in megabytes. Sometimes they ask you to convert to megabytes if your answer is in bytes. And they do that quite frequently. Now here's the thing. You're not allowed a calculator on the exam. And if you're really, unless you're really, really good at math, it's going to be pretty hard to actually convert from bytes to kilobytes to megabytes and so on. So like dividing by 1024 can be quite hard. Now, the good news is, I had a look at the mark schemes for all the papers, and it says that it's totally fine to divide or multiply by 1,000 to convert. Yay! We're saved. All the people who are really terrible at math are saved. Alright, so we're not going to be doing that in the video though, because we want to be true. But you know, if you really can't convert using 1024, you could just do 1,000. Like that's what I'm going to do, because I cannot, for the life of me, cannot divide any number by 1024. I can do 1,000 because it's just moving the decimal, but 1024, nope. All right, so it's 1024 times 512 times 3, and remember the times 3 is from the colors, RGB, and that gives us 1,572,864 bytes. Converted into kilobytes, so we divide by 1024, that gives us this, divide that by 1024, and that gives us 1.5 megabytes. So I'm just going to throw in a random question here. It's not really random, it's good for your learning. We're going to throw in a JPEG compression question. So this file goes through JPEG compression, and it's compressed by a factor of 12. Oh yeah, if any of my calculations here are wrong, then just, post a comment or something, and then I can use annotations to edit it. Anyway, it's compressed by a factor of 12. Calculate the new file size of this image in kilobytes. So you got to be careful when they say in this many or this in this this unit, because what I wouldn't say most people, because I don't know if people do this, but what people could do is they don't read the question properly, so they say, oh, okay, let's compress this by a factor of 12. There, this is the answer in megabytes. But no, you have to be careful to what they say, and it will follow what they say. So let's convert it to kilobytes right now. So 1.5 megabytes that we had last time times 1024 gives us 1,536 kilobytes again. Then we can compress it by a factor of 12 by dividing it by 12, and we get 128 kilobytes. Nice.